Hi everyone. So today we're here to talk a little bit more about the derivative. So we have seen that the definition of derivative is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Now I want to review some special types of derivative notation. There's different types and they each have their pluses and minuses. F prime of x is the one you're going to see most often. It's read f prime of x, or the derivative of f at x. It's the most common form. It identifies the independent variable as x. It's one of the ones that I like. Sometimes you'll see y with the prime on it, y prime. It's nice and brief, but it doesn't tell you the independent variable, what you're taking the derivative with respect to. dy dx, or the derivative of y with respect to x, it names both variables and uses d for derivative. So it tells you that the dependent variable is y and the independent variable is x. That's the other one I like. You'll find that I tend to use these two forms. Every once in a while I'll use this form when we're learning a rule, okay? This is also very similar. df dx, or the derivative of f with respect to x, it emphasizes the name of the function. So if the name of the function is f, it's really the same thing as dy dx. Then d dx of f of x, or the derivative of f at x, it's really the same thing as the one above. It's just a different way of writing it. It emphasizes the idea that differentiation is an operation performed on a function f defined in terms of x, so that this is not something different. This is a function. Derivative is another function being performed on a function, which would need a chain rule when you have to do more than one thing. Now, also important to realize is that all four of these things mean the same thing. Instantaneous rate of change of f of x at a point, the slope of the tangent line to the graph of f of x at a point, the slope of the curve of f of x at a point, and the derivative of f of x at a point. All four of these things mean the exact same thing. Really, really, really important. Next up is linearization. And we graph y equals sine x on each of these given viewing windows. So we're going to go to the TI Nspire right now. Okay. So what I'd like to do is we're going to put in a graph screen, and we're going to graph f of x is sine x, which is a nice trig curve, and you're all very familiar with this curve. Nice and simple, right? But we're going to go to menu, and we're going to window zoom, and we're going to change the window settings. This time I'm going to go from -3 to 3. And I'm going to go from -3 to 3. Okay, now we're looking at just a little bit, not even a whole complete cycle of sine curve, right? Because it would have to go to 3.14. All right, so we've zoomed in a little bit. Let's do that again. So I'm going to window zoom, window settings. This time I'm going to go from -1 to 1 and -1 to 1. Look at how it's straightening out. Now you can only see a slight curve here and here. Now I'm going to, right, because it doesn't look like a sine curve, I'm going to go to window zoom and window settings again. This time, -0.1 to 0.1 and -0.1 to 0.1. I have zoomed in so much that it looks like a straight line. And if I was to hide all these numbers again, I bet, well, it doesn't want to hide. And if I hid this, hide the label, if I hid everything and I just gave you that picture, you would all tell me that I showed you the graph of the line y equals x, wouldn't you? You would all think this was the graph of the line y equals x, not knowing that it's zoomed in on the sine curve so much that it looks like a straight line. And what line does that look like? It looks like, since I'm zooming in on the center here where we're at x equals 0, it looks like the tangent to the sine curve at 0, which happens to be the line y equals x. If you have a differentiable function and you zoom in enough, it's going to look like a straight line. That is called the linearization of the curve. So we have just linearized the sine curve. Who knew a sine curve could look like a straight line? Okay, Now, why is it important for us to find tangents to curves? You guys always ask, why do I need to know this? Well, in mechanics, the tangent determines the direction of a body's motion at every point along its path. So when you have a particle in motion, the tangent line actually determines the direction of the motion at every moment. In geometry, the tangent of two curves at a point of intersection determines the angle at which the curves intersect. We can find the angle at which two lines intersect. You haven't been able to determine the angle at which two curves intersect before because you need their tangent lines in order to do that. In optics, the tangent determines the angle at which a ray of light enters a curved lens, like when you go to find glasses, optometrists and things like that would use this. Now, I will tell you that the problem of how to find the tangent to a curve became the dominant mathematical problem of the early 17th century, and it is hard to overestimate how badly scientists of the day wanted to know the answer. Descartes went so far as to say that the problem was the most useful and most general problem, not only that he knew, but that he had any desire to know. That's how important this question was to the scientists at the time. Let's try a nice, practical, analytical problem so we can practice how to use this. I know you've done this last year in pre-calc, and if you remember doing this at all, it wasn't the calculus that was difficult, it's the algebra. So pay careful attention to your algebra. So we have the function f of x is x squared plus 3x, and we're going to use the definition of derivative to find the derivative of f of x. So we start with our definition of derivative. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h equals the limit as h approaches 0, and I'm going to open up brackets for my f of x plus h. Every place there was an x here, we have to put x plus h. So it's the quantity x plus h squared plus 3 times, instead of x, we put x plus h. That's our function f of x plus h minus our original function f of x, which is x squared plus 3x, all over h. Now we have a bit of algebra to do. We have the limit as h approaches 0. Now we're going to square x plus h. Remember, that's x plus h times x plus h. Okay, you have to distribute, not just square the first and square the second. So we're going to have x squared plus xh plus xh plus h squared plus, now we're going to distribute the 3x plus 3h. Now we're going to distribute the subtraction, minus x squared minus 3x all over h. Now we've got this limit. Notice I keep writing this limit as h heads to 0 because I have not taken the limit. This is a function. I have not done that yet. However, when I look at my algebra, x squared minus x squared is going to add to 0. Also, 3x minus 3x is going to add to 0. I also have here, I have an xh plus an xh, so that's 2 xh's. Then I have an h squared, and I still have a 3h all over h. Now you should notice that every single term has an h. Should happen. We're going to factor out that common h up top, and those h's are going to divide to 1, which is going to leave me with the limit as h approaches 0 of 2x plus h plus 3. So now I can do substitution, 2x plus 0 plus 3, which means that my derivative of f of x is simply 2x plus 3. Ta-da! Now, if I want to find the slope of f of x at 3, remember the slope of the curve is the same as the slope of the tangent line, which is the same as the derivative at 3. So it's just 2 times, we're going to plug the 3 in for x, plus 3. We're just plugging 3 into that derivative. 2 times 3 is 6, plus 3 is 9. Now, we're going to write the equation of the tangent line. Now remember, a tangent line, a line y minus y1 equals m times x minus x1. That's everybody's favorite form of the equation of a line now, right? If you didn't get converted during pre-calc, I will convert you this year. This is your favorite form of the equation of a line. We know that the x value we want is 3. We need a y value, and we need a slope. We just found in part B that the slope, which is the derivative at 3, was 9. We need to find the matching function value, though. If we know x is 3, to find the function value, we plug the 3 into the original function, which means, where was our original function? 3 squared plus 3 times 3, so that's 9 plus 9, which is 18. So now we have y minus, our y value is 18, equals our slope is 9, times x minus our x value is 3. This is our tangent line, and this is perfect. Now we're going to check this with our TI Nspire. So in f1 of x, we're going to put the original function, x squared plus 3x, and in f2 of x, we're going to put our tangent line. But what we need to do, we'll put the right-hand side, and we have to move that minus 18 to the other side, so we add 18. There is no need to distribute the 9 and combine like terms. Don't make more work for yourself, because that only leaves more places for mistakes. Now let's go get our graphing calculator and see what happens here. Okay, so we're going to add a graph page. And here's my graph. So we're going to put in the function x squared plus 3x. And then we're going to put in our tangent line, which is 9 times the quantity, x minus 3, close it, plus 18, and hit enter. I'm going to move this and move this. I need to, can't see our function here where they meet. Oof. Let's try menu, window, zoom. Let's zoom out. Okay. Escape. Let's narrow this a little bit. -20. And let's say 10. Okay. So here we have a picture where we can see our parabola and we can see our tangent line. And let's actually put menu, geometry, points and lines, intersection points, and we're going to click and we're going to click. There it is, escape. Okay, so we've got 318. Now, you can also check to make sure that your tangent line is correct. If you go to menu and you go to analyze graph, we have 5 for dy dx, and if you click here and you hit position is down here where it's asking what the position should be, type in, we wanted this one x is 3, and hit enter. There it is. There's the slope. So that is the slope that we found. Okay, so we know that our derivative is correct at 3. We can also check, we go to menu, geometry, points and lines, and look, here's a tangent line. So we click tangent, and I'm going to click on the parabola. All right, and notice I can't quite tell where I am, so I'm just going to click over here just so I know where it is. I'm going to hit escape so I'm not still clicking tangent lines. I'm going to move the line here, and I'm hovering over this so it says point on, and if you control menu, you can show coordinates and equations. All right, and I'm moving this so I can see it. I'm going to double click the x value and change it to the x value that I want. It now moved both the point and the line. Okay, and you can see that it lines up right on our tangent line. So we know we're correct here, that this equation is equivalent with this equation. You can do that algebra and see that they're the same also. But this way you can check. One more thing I want to do, I want to zoom in, and I'm going to zoom in on that point of tangency. And notice what's happening to the curve and the tangent line. They're getting closer and closer, and as the window gets smaller and smaller, we have zoomed in. Can you even see the difference between the curve and the line anymore? No, you can't. That is the linearization of the curve. I have zoomed in on that point of tangency, and now the function looks like the tangent line. So we have done a lot today, guys. We've worked with the definition of derivative algebraically, and we've talked a lot about tangent lines and the linearization of curves. All right, guys, have a great day, and I'll see you soon. Bye.